Have you ever looked at a polymer datasheet and wondered, how do we actually know the molecular weight? Behind every chromatogram lies a story of calibration, precision, and chemistry. In this session, we'll uncover how GPC calibration standards transform raw chromatograms into meaningful molecular weight data, and why calibration is the key to analytical confidence in polymer science. GPC, or gel permeation chromatography, doesn't truly weigh molecules. It separates them by size in solution. Larger molecules elute first. Smaller ones travel more slowly through the column's pores. What the instrument actually records is elution volume, producing peaks that reflect how big each molecule appears in solution. Calibration standards act like molecular yardsticks, telling the system this peak corresponds to this molecular weight. Without them, we'd just have a pretty curve, but no numbers we can trust. Calibration standards are the backbone of accurate GPC. They translate elution volume into molecular weight by forming the calibration curve, the bridge between chromatographic behavior and true molecular size. Think of them as a bilingual dictionary that lets the instrument speak both chromatography and chemistry. Without proper calibration, the data may look fine, but the numbers can be misleading. Not all standards behave the same way. Polystyrene standards are well characterized, easy to dissolve, and available across a wide molecular weight range. They're perfect for general polymer analysis, as long as your sample behaves like polystyrene. But when you're working with biopolymers or PEGylated drugs, PEG standards are more realistic. They mimic how these hydrophilic molecules move through the column, reducing hydrodynamic mismatch. The rule is simple. Match your standard to your sample's chemistry. Otherwise, calibration becomes guesswork. Creating a calibration curve is like drawing a molecular map. First, inject a series of standards with known molecular weights, recording each one's elution volume. Then, plot log of molecular weight versus elution volume. The resulting line slopes downward. Larger molecules elute first, smaller ones later. Finally, run your unknown sample and compare its peaks against this curve to determine Mn, Mw, and Pdi. It's simple, elegant, and astonishingly powerful. Now let's talk about what really makes or breaks calibration. Use freshly prepared standards. Degraded solutions shift retention times. Always match solvent, temperature, and flow rate between calibration and sample runs. Ensure traceability. Don't mix standards from different sources unless their data are certified. Regularly verify column performance with a mid-range standard. And if your polymer's chemistry differs from your standard, use universal calibration with dual detection, refractive index plus viscometer, or MALS. These small habits are what separate everyday data from publication quality results. When polymers interact differently with solvents or columns, traditional calibration can fail. That's where universal calibration steps in. It uses the Mark-Howink relationship to link intrinsic viscosity with molecular weight, allowing calibration independent of polymer type. By combining detectors such as RI, viscometry, and MALS, scientists achieve absolute molecular weight with no bias from the standard's chemistry. This method is the gold standard for biopolymers, PEGylated drugs, and complex copolymers, where precision truly matters. Even experienced analysts can slip up. Common errors include relying on a single point calibration, ignoring solvent compatibility, or running samples on an aging column. Skipping revalidation can quietly erode data accuracy over time. The fix is simple. Use multiple standards covering your entire molecular weight range. Confirm that standards dissolve completely. Performed routine column maintenance and schedule regular calibration checks. Remember, in GPC, accuracy depends as much on discipline and care as it does on mathematics. Let's bring it to life. Imagine developing a biodegradable polymer for controlled drug delivery. Your formulation's release rate and degradation pattern hinge on molecular weight distribution. Accurate calibration ensures your results are defendable, whether for FDA submission, patent filing, or academic publication. Modern multi-detector GPC systems, combining RI-MALS, UV and viscometry, provide absolute molecular weights, trusted by both R&D labs and manufacturing quality teams. Calibration, done right, connects scientific discovery with industrial reliability. To wrap up, GPC calibration isn't just a checkbox. It's the foundation of molecular truth. When properly executed, it allows us to see beyond peaks and numbers, to truly understand structure, stability, and performance at the molecular level. Behind every reported value lies a blend of chemistry, calibration, and craftsmanship. If you'd like to keep exploring polymer analytics, calibration methods, or advanced GPC techniques, hit subscribe and continue this journey into the science of molecular measurement.